Working? Yes. Some of these I'll have to do in a couple pieces, like 30 minutes and then another one like 15 or 30, so it'll be kind of broken up. When I do the lecture captures and I'm in front of my computer, I can do them all at once. Those are just all at once, but like these, I can break up. Okay, action potential, release of neurotransmitter. This diagram looks horrible, sort of, but there's my little neuron. I kind of drew one. Mine's fatter, a little more clear maybe. These are synapses. They release neurotransmitters, different types, right? They activate. This is the neuron of interest that we care about. What's going to happen? Is it going to fire or is it not going to fire? This goes over in words, kind of what's happening. Now, overall, what I didn't mention when I said neurotransmitters released down at those boutons or axon terminals is when an action potential reaches down there, this charge, this flow of charge, positive charge, it actually opens voltage-gated calcium channels. Calcium at those little terminals, when calcium rushes in, that causes exocytosis and release of neurotransmitter. And this is by exocytosis, that little boring kind of bulk transport. Remember I said it's really important actually for cells in the body. Endocytosis and exocytosis are vital. This is where it's vital. That causes release of neurotransmitter. It opens channels that are either gating positive ions or gating negative charged ions. That causes ultimately opening of sodium channels, opening of potassium channels, conduction of action potential. We're going to go through those steps right now. But it triggers that whole cascade of events that goes zip, 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 and that's how the neuron actually fires. So if we blow up that synapse, does that make sense? Everybody so far? Okay, if we blow up that synapse, mitochondria down here, there's cytoskeletal elements, intermediate filaments, microtubules to help get all the synaptic vesicles down there. They are docked and stored and waiting. So when a nerve impulse fires and charge flows down, it causes the inward influx of calcium through calcium, voltage-gated calcium channels. This calcium actually binds to proteins and helps these fuse to the plasma membrane. There's a whole series of steps that took a lot of time to work out. But basically, impulse, calcium rushes in, causes fusion and exocytosis. That exocytosis releases neurotransmitters, and what they should have drawn are little specific receptors that respond to those neurotransmitters. Then now that can change the charge in this postsynaptic or downstream cell, and it'll determine if it fires or not. So voltage-gated sodium channels, these are the ones that really do it. If the membrane potential depolarizes to minus 55, you see I did that little blip there, I went doo-doo, and then it flew up. If the membrane potential reaches plus 15 millivolts higher than where it started, approximately minus 55, we call that threshold, and that is the voltage that opens voltage-gated sodium channels that are all clustered right there at the axon hillock. And if those sodium channels all pop open at a minus 55 approximately millivolts, sodium rushes into the cell and the cell depolarizes. Okay? Sodium rushes in due to its electrochemical gradient. Membrane potential climbs towards the ENA, or the equilibrium potential towards NA. Notice that when we come in, here's threshold. If we add onto our diagram here, that point is called threshold. Okay? And if we reach that, these ion channels, the sodium voltage-gated sodium channels, are going to pop open, and sodium is going to rush into the cell. And I'm going to use this sort of in two different ways. Instead of drawing it all right there, put it right here. I'm going to act like this is the inside of the cell and this is the outside of the cell. So diagrammatically, sodium channels pop open at minus 55 millivolts. Sodium rushes in, causes the positive depolarization. This right here, we call this peak the action potential. So it goes up, boom, hits, and then we're going to look at what happens after that. Okay? So this is due to the inward flux of sodium through voltage-gated sodium channels. And what is the ENA? What is the equilibrium for sodium? No. Equilibrium potential for sodium plus 62 or 66, depending on the concentrations you're using. Well, this goes up to plus 30. This is a plus. It is creeping towards the ENA, right? Equilibrium for potassium, because sodium is doing what it is able to do based on its gradient, its electrochemical gradient. The interesting thing is these particular channels, they open at about minus 55. They deactivate, so they close. They actually have a gate, and there's a little gate, and there's like a ball and chain sort of function. So they close, and then they deactivate. In other words, they're not just closed, they're deactivated. They have to reset a period of time before they can even be activated again. So at around plus 20, plus 30, they start to deactivate. they close, they swivel, no more sodium's getting through there. Hence, stop the inward flow of sodium and depolarization. That is the peak that's reached. So the deactivation took a lot of time to work out as well. There's actually kind of a little ball and chain on a lot of these voltage-gated ion channels, where they don't just close, reaching that voltage, but there's a ball kind of gates or shuts it. So it will have to swivel away and then be able to be reset again by the proper voltage later. So they're closed versus deactivated or inactivated. And there's a refractory period where it can't open again, okay? Minus 55 to plus 30 opens, pop, 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 all the sodium channels open. Sodium rushes in. That's the peak reaction potential. Okay, now what happens on the downward sweep? Potassium comes into play, voltage-gated potassium channels. So at about that same voltage, and actually a little before that, the voltage-gated potassium channels change and they open with a high voltage. So around 25, 30 millivolts, they pop open, potassium rushes out, following its electrochemical gradient. So now potassium's leaving, because I'm opening potassium channels. Where's potassium going to go? It's going to leave. So I'll use those black here. Potassium now goes, whoop, okay, voltage sensitive, popped open. Potassium is leaving. It's going out. That makes it go back negative. It makes it repolarize. Matter of fact, it keeps going out because they stay open a little longer. They get activated around 25. They don't start to close until they get down like minus 80, minus 90. So potassium is still leaving, causing that hyperpolarization. Okay? Makes the cell repolarize back towards potassium's EK. What is potassium's equilibrium potential? Minus 90, and actually, look at this, goes to about minus 80. It almost gets there. Some cells it gets like minus 85. It goes to like exactly the equilibrium of where potassium would go based on its concentrations inside and outside. This is just demonstrating hyperpolarization. We can measure depolarization. We can measure if you put on a stimulus that's an inhibitory versus an excitatory stimulus or neurotransmitter. If you can get it high enough with the stimulus to threshold, it will fire. So if a cell, muscle, or neuron reaches threshold, it comes down to the physics of ion channels. Those sodium ion channels will pop open up their gate, and sodium will rush in. And if that happens, we call this event. What do we call, if it reaches that minus 55 millivolts threshold, and then something happens, what do we call that? Action potential. And it's all or none. That means if we get there, oh, that sodium is rushing in, that's it. Those are open. And now there's going to be more of them. And they're actually going to kind of spread inside of the cell and go open additional ion channels because more charge is coming in, right? And it's opening more adjacent sodium channels at those nodes. So it fluxes in and moves real fast. So sodium is rushing in. We call this all or none. It's not graded. It's not going to, a little bit more. If it gets threshold, it's firing. That's it. So here it is. I've already done this, right? Minus 70, minus 55, AP, hyperpolarized, comes back up. Now, what's responsible for getting the membrane potential back to RMP? And this is due to ion channels operating in different ways, right? Responding to voltage. If neurotransmitter causes charge change and it's enough, this will either happen or not, right? But what is responsible for getting the cell back to where it likes to be happy? Homeostasis, that RMP. Sodium. Nope. There's a specific thing that keeps that cell at resting membrane potential. Nope. You've already learned about it. We talked about it for a long time.
Integrins?
The NAK ATPase pump. Remember, that's where we started. Came all the way back there, okay? That is what restores it and makes it sit happy right there, okay? But if it gets a stimulus, it's going away from there. But then the NAK pump is like, whoa, we gotta back to where we started. We gotta, okay, get the sodium out, potassium in, sodium out, potassium in, and then we get back where we're happy, minus 70. Yes? Okay, all right. So that's the action potential. I just summarized the same thing I just went through kind of physically. Minus 55 is threshold, voltage-gated NA channels fly open, sodium flies in, cell depolarizes, more and more sodium channels open because they're voltage sensitive. So the higher the voltage creeps up, the more of those channels have a robust response and more of them open. the cell becomes more and more permeable to sodium, sodium ion currents rush into the cell. We call that a positive feedback loop, where the stimulus or the change causes more of that same thing. More and more and more and more until you, boom, you get all the way to the top, and then they start deactivating, start closing, so no more comes in. So you're maxed or peaked out at the action potential. Causes the overshoot of resting membrane potential, so it goes way up. Membrane potential reaches approximately plus 30 millivolts. That depolarization at its peak is what we call the action potential, or firing. That's how a neuron or a muscle cell fires an impulse. All right, so at plus 30, sodium channels close, potassium channels open, potassium flows out. So then it goes ding, 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 goes down the other way. Results in the repolarization and then hyperpolarization of the membrane. We call that a negative feedback loop because that stimulus or that change caused the reverse to happen, right? So it went up real high, okay, now we're gonna bring it back down. So it's a negative feedback loop in this part of the action potential. Repolarization actually undershoots the resting membrane potential, and so it gets often to about minus 85. That is very close to potassium's equilibrium, right, which is minus 90. Is it still working? Someone call me. Oh, can you hit snooze? Doesn't matter. I mean, it doesn't show it on the videos anyways. It's happened to me before. Doesn't reach potassium equilibrium potential because voltage-gated potassium channels get inactivated as the membrane potential falls. So as they're falling and getting to lower charge voltages, they start shutting. So it doesn't get all the way quite to the minus 90. NAK pumps are the ones that quickly reestablish membrane potential. So where do the NAK pumps come in handy? Here and here. They are maintaining the neuron sitting at rest where it likes to be. This is kind of a mess, but it goes through what I've just described and drawn and stuff for you in step 1, 2, 3, 4, 5, showing you what I drew right there and labeling and phasing. I find this a little bit much, but I sort of like this is a much kind of cleaner, I bias it's mine, but I feel like it's a little more descriptive of physically what's going on. I don't know. You can watch the movie. I mean, if you guys have to leave and skedaddle somewhere else, I'm just gonna.
Voltage-gated channels open and close in response to an electrical voltage, so they are affected by changes in electrical charge around them. When a neuron is at rest, a charge difference is maintained between the inside and outside of the cell. This charge difference is produced and maintained largely by active transport using sodium-potassium pumps. The pumps send sodium ions out of the cell and bring potassium ions in. While other channels allow some flow of potassium ions back out of the cell, the sodium ions cannot easily get back in to replace the lost positive charges. The overall result is that the exterior of the cell has a net positive charge and the interior has a net negative charge. The difference in charge between the interior and exterior of the cell is called the resting membrane potential. A nerve impulse begins when a stimulus disturbs the plasma membrane on a dendrite, causing sodium channels to open. Sodium ions flow into the cell, lessening the charge difference at that location. If the change is enough, it will cause nearby voltage-gated sodium channels to open. This allows so many sodium ions to flood into the cell at that location that the membrane there is depolarized, with the local region inside the cell having a net positive charge and the outside of the cell having a net negative charge. This affects neighboring voltage-gated sodium channels, which then open, moving depolarization along the membrane. This moving depolarization is called an action potential. Changes occur behind the action potential to restore the resting membrane potential. The voltage-gated sodium channels close and voltage-gated potassium channels open. This allows a rapid flow of potassium ions out of the cell, repolarizing the membrane so that the inside is again negative and the outside positive. This is followed by use of sodium-potassium pumps to fully restore the resting membrane potential and to reestablish proper concentrations of sodium and potassium ions inside and outside the cell.
Okay, and then, okay, so I'm just gonna stop right there, because I was doing a lecture capture like a live lecture capture. Pause That's it.